This is part 2 of our class meeting video, and what we're looking at here is connecting the online simulation that you did for energy forms and changes, and we talked about this in part 1, and we're trying to connect that to the style of question that's in the textbook, and the textbook focuses on doing work on an object to change its form of energy, if you will. So, not to get you too dizzy going back and forth, but one could argue that this girl on the bicycle, she's doing work on the wheel of the generator. But with it being a continuous application of the energy, her continuously working on that wheel, so to speak, it seems to take on a different look. These are still great problems because we're looking at energy forms and changes. It's not all mechanical. We're looking at electrical. We're looking at chemical. We're looking at light. So those are awesome problems, but they invite a little bit of a different analysis than the ones from your textbook. So in the part 1 video, we looked at doing work on this box to lift it and giving it gravitational potential energy. With that comes some equation type problems and some other concept understanding. So in this video, we'll focus on those. So what do we call the quantity force times distance? And I'll leave this, begins with W in here. I'll leave that in on your quiz. That just orients you to the content. So we're talking about work, the precise physics definition of work. The units of it for us will be joules if we're applying a force in newtons over a distance of meters. When you do work on an object to lift it up, what quantity of the object do you change? That term there comes right from your book homework. And so as we look at the crane lifting the object, we're realizing that it's getting potential energy. I think I'll also leave the P and the E here for you as well. Potential energy. Whoops. All right, we'll go eraser. And the other situation that we're going to be considering in this content is when we do work on an object to cause it to accelerate. So the scenario is always going to be some toy car with frictionless wheels, and we're going to be able to apply a force to it over a distance, and we'll give it kinetic energy when we do that, energy of motion. So in the reading from your text, I would have imagined you would come across those terms, potential energy and kinetic energy, quite a bit. All right, moving to page 3. I like these headings here because one says use your conceptual understanding. You could do it with an equation. It may not be necessary, and then we get to some equation problems here. These are like the ones that were presented in your textbook. Okay, work is required to lift a barbell. How many times more work is required to lift the barbell 4 times as high? Well, I'm going to resist studying the application to answer that. I'm just going to lean on a conceptual understanding that if I'm lifting a barbell 4 times as high, then I'm doing 4 times the work. Okay, now we get into some equation ones. This will be available to you during any assessment. Number 5, which requires more work, lifting a 10 kilogram load a vertical distance of 2 meters or lifting a 5 kilogram load a vertical distance of 4 meters? Having given you the equation, there's actually a huge part of me that just wants to do this conceptually. So I look at the mass of the load and the height that I'm lifting it, and then I see that I've got half the mass for this other load, but I'm lifting it twice as far. So using my intuition, I want to say that those require equal work. And we'll actually see that using the equation, but it will be a little bit tougher to use the equation because technically these are masses, and I need to plug the force that's applied to the object in here. So I know my answer because I analyzed it conceptually. But now I'm going to use the equation for it. We talked about this earlier in the year. If you want to know the force of gravity acting on an object, it's always 10 times its mass in kilograms will get you the force of gravity in newtons. So this load here is really a 100 Newton load. And this load here is a 50 Newton load. So if the force of gravity acting on the load is 100 newtons or 50 newtons, then to lift it at constant velocity, I've got to apply that force lifting it up. So that's where that comes in, and I think we'll have to work on that a little bit more in class. But for our purposes right now, we're going to apply a force of 100 newtons for 2 meters. And so when I do that for this one, I'll see if I can get some different colors going here. So for this first box, that's going to be 100 times 2, so that's going to be 200. And newtons times meters gives us joules. And then the second box is 50 newtons, a distance of 4 meters, and 50 times 4, that's also going to give us 200. And when we multiply newtons times meters, we get joules. And so there we see that indeed our intuition was right, that the work required for each of these is 200 newtons. So we'll say which requires more work. We'll say the same amount of work. Same amount of work. Okay. A 10 Newton block needs to be lifted up. How many joules of work are done on this solid block when it is lifted 3 meters? I like this question. This appears more straightforward than the comparison one in number 5. So I get to more directly say, oh, okay, I'm going to apply this formula. Work equals force times distance. The force that I'm going to apply is 10 newtons. As much as I generally encourage writing units in here, I'm going to back off of that for this. The force is 10, the distance is 3. So the quantity is 30, and then I need units. And so I'm going to appreciate that I took a force in newtons and multiplied it by a distance in meters, and so that's going to give me 30 joules. I'm at 8. Well, I've got one more question here, so let me scroll up. I'm a little time sensitive here. What is the change in potential energy of the toy car after the push? I think I have a little editing issue there. So I'm going to cross that one out. And I think we've covered a decent amount here. So anything that we didn't cover in this video, we'll leave for another day. Thank you.